what I will be talking today about is Spark-Cypher, and specifically about graph analytics in Spark, what it can do, what are some useful modules, and how those will or will not be integrated in Spark-Cypher. This talk will contain one major plot twist, see if you can spot it. But since we still have a lot of time, let's start with something mildly boring, which is history. So Spark has been with us since the early 2014, where Spark 1 was officially released. Of course, there were versions predating that, but this is the, say, official, onset of the Spark era. And nearly exactly 2 years after that, we've seen the first of Spark 2. So we went from, using RDDs to data frames, first more pervasive use of Spark SQL, Spark ML replaced MLlib, all those nice things, right? Within the span of 2 years. And now, 3 to 4 years onwards from that, the preview version of Spark 3 has been released. One thing that I noticed, which is particularly relevant to my thesis here, is that Spark is the kind of framework that is really quickly adopted in the industry. Well, the way I see it, this is because Spark 2 was, its main claim to fame was that it was almost 10 times faster than Spark 1. And so that really worked in terms of the institutions that basically believe in the fact that fastest analytics wins, and that being able to perform more analytical insights to have them available at hand faster gives you the competitive edge over your competitors, like we see, say, in the banking sector, which, because of my company, I'm fairly familiar with. And companies, let's say, like Uber, did this thing where they tested Spark 2 even before it was released, and adopted it officially very quickly after the release. And if you're still not convinced, there is a fact from our practice as a consulting company here in Poland. 2 years after the release of Spark 2, we only really had one project that was still done in Spark 1. Everything else was done in Spark 2. And right now, 3-4 years, we have no Spark 1 projects. So if you compare that to, let's say, I checked that a few days ago, and Spring 5 came out just a year after Spark 2, it's nowhere nearly as, let's say, an industry standard for doing Spring applications than Spark 2 is in the Spark world. So this thing with, new version of Spark coming up, being faster and being really quickly adopted, it's a thing. And so now Spark 3 is coming. And again, the claim is it is up to 17 times faster, so even better improvement than Spark 2 brought us. This is given by Alibaba, who did some initial runs on the TPC-DS benchmark, so fairly popular benchmark that simulates the data-driven decision-making systems. And so what I'm saying is Spark 3, just like Spark 2 has been, it will probably be quickly adopted. And it is worth actually studying and learning even right now before it's officially released, because once that happens, the adoption will be very quick. And in a year or two, we'll all be doing Spark 3. And of course, it also comes with some promising set of new features, things like optimizations in terms of adaptive query execution and dynamic partition pruning. GPU will be available as a usable resource, so you're looking at all the tighter integrations with things like TensorFlow and those deep learning libraries. They claim they fixed the Kubernetes support. That one I have not tested myself, but well, it certainly seems interesting. And among the features that were supposed to come with Spark 3, of course, this is the talk of the day, Spark-Cypher. So the point is, we were promised with Spark 3 some additional functionalities in terms of graph processing. So let's now take a step back and think about graph processing, about these common and uncommon usages. Of course, we all associate graph processing with those very common cases for it, like mining social networks, like monitoring packages in the actual networks, simulating road traffic, performing all sorts of really real-life network simulation, routing, packet tracing, and recently you have those things like contact tracing or monitoring viral spreads in the age of coronavirus. Just as a side note, if anyone would be interested, during the QA session, I can link you a very nice graph simulation that was done for this. And I mean, it was done before the thing really happened in Europe, but predicted the spread pretty well there. And for those common usages, there is a common set of algorithms that you always want to have with your graph processing, graph analytic libraries. Of course, that there's more than the 4 that I will show, and I don't even have that much time to mathematically explain how those work. But we all can look them up, and the basis you can probably also get from those pictures. You have things like your connected components and strongly connected components for finding closely associated sections within the graph. You have PageRank, which is used by Google for ranking pages based on the principle that the page that is linked to by the most is the highest ranked one. You have things like triangle counts, which are again good for identifying clusters in things like, for instance, social networks, and of course the algorithm that we all did.
Kamil, sorry to interrupt. Could you maybe try to move this pop-up from StreamYard so it doesn't cover your presentation?
Yeah, sure. Let me try to move it, but I don't think I can move it actually.
There is a hide button. There is a hide button on it on the right.
Yeah, but I think it's really floating above the presentation. I'm not sure I can do anything with that because it seems like my cursor is behind that instead of above that.
All right. Okay, then I guess we will just have to live with that.
Yeah, I'm sorry, but I'm not sure if let me try again. But again, it's like I switch. If I'm trying to click the hide button, it's just switching the slide. Sorry for that.
Okay, no worries. Please continue.
I'll try to be mindful of that, and if there's gonna be all hovering over something, I'll try to maybe read it out loud. I'm sorry for the inconvenience. Yeah, so as I was saying, in terms of those common algorithms that I wanted to enumerate, there's of course the one that we all did, in the first year of our studies, the Dijkstra algorithm. But for those for whom that was a long time ago, it's a basic greedy algorithm for finding the shortest path in a weighted graph. And this is all good, meaning that for common cases, we have common algorithms, and if we're investing in a graph processing framework, we just want to have them there, right? To be able to reuse them for those cases. But taking the time, I wanted to also go into graph processing for more generic cases and from maybe a slightly philosophical standpoint. Because we all generally think of a graph as a, this visualization where you have circles connected together by arrows or by just straight lines, and that symbolizes the graph, right? But can a graph be represented as a two-dimensional matrix of real numbers? Can it be represented as a function defined over a Cartesian product of two data sets? Of course, the answer to all of those is yes, and here you essentially have it shown on a very simple example, right? All those three representations, they're equivalent to each other to a symbol of a very simple weighted graph, undirected weighted graph in that case. And what that gives us is we can say that we can use sometimes the graph representation for some sort of problems that we don't initially associate with them, and it might actually be beneficial. For instance, if you think about collaborative filtering, right, which is the algorithm used by Netflix and similar content providers to suggest content to you, computationally, that's a matrix calculation problem. But the way it works is it's try to find the people that like the same things that you like, and then when it needs to guess what your opinion will be of a particular piece of content, it looks to those people and tries to guess what your answer would be based on their answers. So computationally, that's matrix calculations. But if you were, for instance, to visualize, let's say you were supposed to visualize the impact of the people that have the similar taste as you are on the content that might be suggested to you, you would probably want to have it in graph form just to be able to show those connections formed there, right? And in that spirit, I want to talk a little bit also about graphs versus tables, because at least few good years back when I started my career, it was still this predominant thinking that most of data storage was done in relational databases. Of course, that's not true per se anymore, but starting with that mindset, many of us are used to basically thinking in tables as a default. And I would argue, and I will try to argue here, that actually there is a lot of problems that we think that are tabular by definition, just simple problems that are not by definition something suggesting routing or suggesting I don't know, finding a subgraph that we tend to associate with tables because we generally associate problems that are not suggesting a different model with tables. But sometimes graphs can actually be a better modeling to solve those problems. So the difference is, in tables, relationships are implicit, meaning they're not really part of the tables, part of the storage model. They're just based on the fact that some fields in one table have the same value as other fields in the other table. And while querying those tables, we have to sort of check for those regularities and therefore form and retrieve those relationships, right? Whereas in graphs, where our model is nodes and relations, and nodes and then those nodes and relations can have their own properties, let's say key value properties, which would be a property graph then, those relationships are explicit. So in cases like, for instance, multi-level searches, graphs generally tend to be easier to analyze than tables. Because, well, I'll show you that on this very, very simple example. So let's say we have people, a collection of people, and we have potential relationships of people being friends with other people, but also some information as to which countries they went on vacation. And we would like to perform this query of finding a person that is friends with X, let's say me in that case, and that vacation in India. That could be useful, to get some travel advice, right? So if you were supposed to model this on entities in tables, you would probably do something like that. You would have a person table, then some table, mapping people to other people in terms of being friends, but also a vacation table that would map people to countries they vacation in. And then on this, you could do this very not simple, at least for such a trivial problem, query, which does 1, 2, 3, 4 joins, right? To retrieve that information for you. So while the model is not very huge, you would have to search multiple tables for those relationships, and essentially the search can become quite costly. Of course, if you imagine that just happening on your local database, you'd probably have optimized joins, and it would not be that terrible. But now let's think, more in terms of how I think in my world, where those tables would probably be some very large data sets from very different data sources read into Spark-SQL, right? So then performing those joins and optimizing them is not that trivial, and this operation doing joins on joins on joins could actually be a very costly one, especially in the world of huge data sets. Whereas if you try to model the same problem on graphs, and again, maybe that's not such a huge difference if you look at those nodes here, but again, this is the, I think, simplest example on which you can see the difference. So bear that in mind. This graph, which essentially shows the same situation, is just easy thanks to the fact that the relationships are explicit. It's just easier to traverse. We just need to fetch this very simple portion of graph, and once we match this and we traverse from one person to the other person, we have the data that we need to fetch, and that corresponds to the query which is written on the bottom of the page in the language called Cypher, which I'll get to in a second, but essentially it will be linked to the topic of the day, which is Spark-Cypher. Yeah, so the point of this Spark is basically saying that sometimes graph modeling can actually be easier and beneficial to solving certain problems, especially, again, those multi-level searches where you cannot leverage that much optimization in tabular form than just defaulting to tables at every turn. And so with that spirit in mind, there came to be something which I just very quickly mention, which were the graph databases. They're part of, the NoSQL family, right? They appeared with the, well, NoSQL was, all the rage. And being NoSQL, they're a bit different from your usual key value or column family or document, in that they're still on the CA part of the CAP diagram. Meaning they're consistent, they generally have good consistency and good availability, but they're not very partition tolerant. So they're more similar to relational databases than any other of those types, which again, if you look at those, the fact that, they have explicit relations and all this, it's not that surprising. And most of those databases, again, because we want to solve those common problems very often, they have in those popular graph algorithms like your PageRank and your Dijkstra inbuilt. And what they're good for in terms of solving graph problems is they're good for storing data, because they usually have some sort of graph optimized storage, and doing things like ad hoc querying. But what they're not good for is usually things like integrating with external data sources, and doing parallel computations, because again, the graph model is not inherently a very partition tolerant one. And according at least to Wikipedia, and well, I think most people would agree that Neo4j was one of the popular graph databases, and it still is, I think, the most popular graph database, most deployed in the world right now. Well, of course, apart from having nice visuals that you can see here, that's the sort of result from a query that you can get in Neo4j. It also has a pretty good connector to Apache Spark. But why it's really important is this. People at Neo4j had to come up with a query language for the database, and so that would be sort of graph native, but also very elastic, and it would enable ad hoc querying and designing very arbitrary graph traversals and executing them. And so what they came up with is Cypher, that you can see an example of on the top of the slide. It's a native language in Neo4j, which is sometimes jokingly called a bastard child of SQL and ASCII art, because, well, if you look at it very hard, those parentheses and those hyphens, etc., they're actually designed to visually look like a, sort of plumpy graph there. I hope that, well, you have enough imagination to see it in there, despite all the text clutter. And so, yeah, let's quickly look how Cypher works, right? So Cypher is very simple, but again, it really can do a lot in terms of ad hoc graph querying. So you have your match, which is essentially like select in SQL, in that you start queries with it. If you want to draw, quote unquote, a node in Cypher, You put it in parentheses, and you assign it to some variable, and then you do double point, and you put a label in there. And the same thing in rectangular parentheses that would denote a relation. And so then you can connect your nodes with your other nodes through relations, either bidirectional or unidirectional. Just remember, in case if you want to do one direction, you just put one arrow in there, not two, which always surprised me personally, but that's how it is. And then if you want to match for some kind of properties, because again, in Neo4j and other places that now support Cypher, it's usually a property graph in that both nodes and relations can have some sort of key value properties. And finally, once you've matched what you wanted to match, you do a return. And you can return either parts of the graph like relations or nodes that you have in your query, or you can do return star, which will return the whole subgraph you matched. So a piece of the overall graph, and that can, for instance, be a useful operation in terms of cutting out parts of the graph and getting them to be further processed by further queries. So yeah, Cypher is simple, but it's very powerful in terms of how you can do ad hoc querying on graphs, and how you can easily design your useful traversals for common problems. Like this example here, this is still finding a friend of a friend who vacationed in India, and more or less it's a one-liner. And so because Cypher is so imperative on one hand and very generic, it started to sort of go further beyond than just Neo4j. In that it's the people at Neo4j, they started the Open Cypher project, where they made Cypher as a language available to be implemented on multiple platforms. And it's already been adopted, for instance, by Redis Graph, which is a graph-based extension to Redis, and to some extent in libraries that were designed for Spark, which again I'll talk specifics in a minute. And Cypher is sort of also the basis for something that they're trying to design, which is called GQL, Graph Query Language, which is supposed to be like a SQL-like standard for graphs. Of course, it's not pure Cypher, or it's not even like 90% Cypher, but you can see Cypher influences in there, obviously, as being one of the most popular graph querying languages. And yeah, so those were Cypher and graph databases. And again, they're good for storage, they're good for visualization, but they're not good for computation. Because if you want to do computation en masse, which is obviously what Spark is for, then what you need to have is you don't need necessarily to have very good consistency, but you need to be able to partition and replicate your data on a computation cluster to make your computations as parallel as possible. And of course, this is kind of a joke, but there is some truth to saying that the philosophy of Spark is essentially throw RAM at it, right? Meaning that sometimes what you do is you have your calculations. They don't perform as much as you wanted to, so you just take them on a Spark cluster, give it a lot of RAM, and sometimes that actually fixes the problem. Again, it's maybe a bit of a vulgar approach to this, but that combined with best practices, that's really tends to work for you sometimes. And yeah, so Spark has a module for graph processing, and it has had it at least since I started programming it in Spark, which was like 2015. So which really fills in that gap of doing not necessarily storage and just ad hoc querying, but more large in-flight computations in parallel on computation clusters, right? The module is called GraphX. You have the logo in here, and yeah, let's see how code looks like in GraphX, right? So let's assume we have a file, a JSON file like this, because what also would Spark be used for probably in the world of graph processing is sort of getting that knowledge there. As mentioned, for instance, in tabular form, your relations, which in Spark you would get from reading files, from querying Hive tables, from getting that data from Kafka, your relationships are implicit, as shown here, where you have references, you have IDs on each record on the top, but you also have references to them in those friend fields, right? So this is sort of a implicit relationship. And you would often use Spark, and you can use the graph extension to sort of analyze the data in order to mine this relationship and be able to encode it in your data, and then maybe save it in a more understandable form, or just load it into a graph database like Neo4j, which has a pretty nice Spark connector, which also integrates with GraphX, so you can directly save parts of GraphX graph to Neo4j at that. And so, yeah, constructing that knowledge would essentially be something like you have on the bottom, where I'm taking an RDD, because one of the things in GraphX is that it is still an RDD-based API. So, good old Spark 1, even like Spark 1.4 days. So I would take those RDDs and perform a series of, let's say, manipulations, like trying to extract those friends and essentially essentially explode the array of friends from each record, and then try to join that with the ID key in another instance of this people RDD to finally build a class called Edge, which is a representation of a relationship in a graph for GraphX. So essentially, the edge is the ID from of the vertex that the edge comes out of, the ID of the vertex it comes into, and yeah, each vertex has to have an ID, and this ID has to be unique. So bear that in mind, because that's, as we know, generating unique IDs on computational clusters, that can actually be tricky. So it's better to have them in the data or improvise. And so once we are able to mine those relationships for you, and we have those people, we can key them by ID and put them as nodes, and those edges, the RDD with the edge case class in it as edges, we're able to build a GraphX graph. And here I'm just, again, reusing this very simple example of finding people who are friends with me, because one thing that GraphX is quite good with is it has a lot of operations that can manipulate basic graph structure. Here is just really collecting neighborhoods. So for each of the vertices in the graph, I'm collecting all the vertices that are directly connected to it. But you also have things like, for instance, filtering operations, or on the node, edge node triplets, or even like a very generic topology operation, which is called aggregate messages, where you can essentially first send messages from each edge. You can decide to send message to the source and target, or just one of them, and then you're able to aggregate those messages at nodes to form yourself a new graph. You also have subgraphing operations, and generally speaking, in terms of the APIs that I will be showing you today, GraphX is the strongest one in terms of directly manipulating graph topology. So yeah, GraphX is officially supported as part of the Spark, Sorry. It enables you to do those graph computations at scale. It enables you to manipulate structure as RDDs mostly. So you can have RDDs of edges. You can have RDDs of vertices, you can have RDDs of those triplets, and you can have multiple structural operations. Out of those popular algorithms that I mentioned, GraphX has some of them available out of the box. There is at least 2 flavors of PageRank, as much as I remember. There is certainly triangle counting, and also called connected components and strongly connected components. So basic, common case algorithms, they're available out of the box with GraphX. And one very good thing is also in GraphX, you're able to change the partitioning of your graph in terms of vertex and edge cuts. So essentially how the data is distributed on the cluster. As we already probably know, sometimes graphs can be tricky in terms of partition tolerance. So you're able to tweak that to fit to improve the performance of particular computations that you're going to be doing, which is something you would expect from Spark. But that said, GraphX also has some ugly parts. First of all, there's the RDDs. RDDs are very much the thing of the past right now. I mean, again, Spark 2 was heavily adopted, and pretty much all Spark projects use Spark 2, right? And GraphX, it's still based on RDDs, and it's not really that actively developed, mostly because of this, right? Has no integration with data frames. And all the querying and manipulations, this is all Lambda based, this is all RDD based. There is no imperative aspect to it. So while you would be able to, for instance, do let's say transformations like, again, aggregate, maybe shrink parts of the graph locally easily in GraphX, if you were supposed to run like a larger version of this graph traversal for multi-level search, actually the GraphX API is not very friendly in that terms. Like, you do not have any facilities similar to Cypher. And also, I wanted to mention that GraphX is only available really in Scala and Java. There is no like Python or R integration because of RDDs. Well, some people say that's how it should be with Spark, but I'm just putting it out there. And so because GraphX was already kind of obsolete when Spark 2 was coming out, so even before the official release of Spark 2, some people in Databricks started working on GraphFrames. GraphFrames were essentially the idea, create something like GraphX, but instead of representing the edges and nodes with RDDs, let's put data frames in there, because data frames, they have way more declarative API, data manipulation, data reading, working with semi-structured data. That's way easier for you if you use data frames, right? However, while it originated almost 3 years ago, and initially I remember there was some, heavy praise on Databricks side and some articles in their blogs, it never actually became a part of Spark. It's still an external library, and its latest version is 0.8.0. On the other hand, it is available in Python. And so let's see how the API differs here, and if it's really all that different. So first thing you can see, again, reading same file, right? Same pieces of data here. You're able to leverage Spark SQL to perform input-output operations, and compared to, reading those files line by line and text, and then parsing it, and then solving all the problems with implicits and not reusable exception, that helps. Then again, you have to do the mining and sort of construct relationships. Essentially, if your data is, if your relationships in the data are not explicit, you have to find them out. And with your data frames for nodes, with your data frames for edges, which now do not have to have any sort of specific class like edge inside of it, can just be data frames that contain some specially marked fields. You're able to construct a graph frame, which basically is like GraphX graph object. And here you can see that the algorithm for finding friends for a particular person will be a bit different, because you don't get all those low-level GraphX topology operations. But what you have is, for instance, you can take triplets as a data frame and directly, for instance, manipulate its fields in Spark-SQL. So let's look at the other part of it, meaning data preprocessing, which some people say it's either the ugliest or the most beautiful part of working in Spark, depending how you see it. So here you can also see that you essentially perform some initial data transformation and then self-join. But you can clearly see that using data frames, it makes it more understandable and gives you higher level API, because we're able to leverage, like I'm using here, the Spark functions. And again, this is just a simple example, right? Again, you have to put in there, you have to still perform that self-join. You have to put in there those special fields like GraphFrame, SRC, DST, and ID. And that thing where you have to mark nodes and edges with unique identifiers, that will not change in pretty much any case of working with Graph in Spark. One thing that might come in handy is because, again, generating those unique IDs is not easy. So monotonically increasing ID can sometimes really come in handy in those cases. So we can see that GraphFrames, while being a step up in terms of how easy it is to work with graph data in Spark, and also having things like those algorithms available out of the box, pretty much one-to-one with what GraphX has in that regard. It never really became official. It's still external library. Those GraphFrame data structures are convertible to GraphX and vice versa. But officially, it never became part of Spark, and GraphX is still the official one. And now, this one thing that I also mentioned that is really useful, but it's also been missing from Spark graph processing APIs for a long time. So basically, the ability to not manipulate the graph topology directly on vertex and node level, but to just write those ad hoc queries potentially in textual form, which is pretty much just Cypher, right? That's also been missing, and well, people from OpenCypher basically wrote this library called Morpheus, which is specifically that. Pretty much what it does is it just gives you Cypher on Spark. Of course, this is, again, a data frame-based API, so you create your Spark session. From that, you spawn a Morpheus session quickly, which is really just the line. And you're able to, well, pretty much, if you look at your data preprocessing, it looks the same. You're able to work with data frames to leverage all the power of Spark-SQL. Then you build a graph, which is, again, very similar, if you look at it, to the way this is done in GraphFrames. I believe Morpheus actually just uses GraphFrames under the hood to implement that functionality anyway. And what it really gives you, and the benefit is, once you build your property graph, you're able to go Graph-Cypher and basically run Cypher queries on your property graphs built out of data frames. And again, same example, you can see that the APIs are quite similar. So the point is, and Morpheus is, since the target is really just to have Cypher for ad hoc querying, for more general forms of querying on, but still being executed on a Spark cluster, Morpheus doesn't really, I don't think it really ships with any sort of inbuilt algorithms. But again, you can combine it with those libraries that do, right? But the point is, so before Spark Free, with those free libraries, we had tools to perform various types of graph processing, from GraphX low-level topology manipulation, but it also being a bit old and outdated API, to not officially supported Morpheus and GraphFrames. But it's also been kind of a mess using multiple of those at once and stitching them by hand. So a lot of people were quite enthusiastic when this came out, which was essentially a proposal to implement one API for property graphs and for running Cypher queries and for running those standard algorithms. So pretty much all the standard functionalities you need to do good graph processing, and just put them into one single API, which was called various names at various times. I believe it was at some point the name was like Spark-Graph API, but also Spark-Cypher. And yeah, that started happening. It was supposed to be released in 3.0. And now the plot twist. So what's the hardest you've ever built trolled? Because for me, I mean, there's been multiple instances, but one of them is definitely this. So like maybe a month ago, when most of this presentation was already done, I sort of opened the new jar for Spark-Cypher, and I noticed it's kind of empty. So I started going through the posts around that Jira in terms of Spark development, and I kind of came across this. So around a month ago, it turned out that Spark-Cypher was descoped for Spark 3, which is now in feature freeze state. So this means that at least for Spark 3.0, Spark Graph or Spark-Cypher will not become a part of the release, and we will not actually get this single API that was supposed to combine all those working features, which is very saddening for me in terms of doing good graph processing on Spark, but unfortunately that's the reality. So what I wanted really to say is the sad answer to the question of how will we be doing graph analytics with Spark from 2020 on is, surprisingly, that will not be with Spark-Cypher. We'll still have to use the existing popular libraries and sort of stitch them together. We will have to use GraphX if we want to have official support, if we want to do more topological manipulations, more collection-based manipulations on those graphs. And of course, I mean, official support also equals stability, right? But if we want to go more on, leverage the power of Spark SQL, for instance, data preprocessing, that has to either integrate with GraphFrames or with Morpheus. And specifically, if we want to do, say, ad hoc querying, I don't know, work on graph structures or build graph structures in things like Spark Shell or notebooks. I know there is a quite good visualization extension on Morpheus for Apache Zeppelin. Then we'll have to use Morpheus, more likely than not. Again, use multiples of those and connect them together, because Spark 3 has now officially resigned from shipping Spark-Cypher with it. The only thing I can really say here is that I'm hoping that Spark-Cypher and a single API that will give us all those benefits and official support from Databricks will still be released in some of the further versions. But for now, not much is known about it. So yeah, sorry for that slightly pessimistic conclusion on this. And with that, are there any questions?
Thank you, Kamil, for the great presentation. As far as I know, there have been there is one question just now from Krzysztof. What, in your opinion, are the best sources to get started with Spark 3 and Cypher?
In terms of Cypher, there is documentation for Morpheus. Well, in terms of Cypher as just a query language, I would go for the very extensive documentation that Neo4j provides. Again, to grasp the basics of Cypher, that's very easy, so that should happen quite quickly. In terms of Cypher on Spark, that's obviously Morpheus. The documentation is not that extensive there, but you can get the gist of it, from the examples and basically, practicing. And Spark 3. So Spark 3, there is some materials released from Databricks, and there's also Spark Summit happening quite soon, where parts of Spark 3 will be the talk of the day, and so maybe also participation in that.
All right, thank you, Kamil. So I guess that's it for the presentation.